All right, let's do this. Let's try to make it fast. All right, what I'm doing is I'm building here's my FPGA with multiple buttons. It's got a 100 megahertz clock. I'm going to press the button. It's going to turn on a light. How do you do this? How are we going to do this? We need a debouncer. And we need a couple of them. We need one for each button. We need a what's that thing called? Edge detector. We need one of them. We need two of them. How'd that happen? Give me another edge detector. Not right there. Not what I wanted. You are being annoying. Edge detector. Okay. And then that will lead to a shift register. We're not going to get into shift registers right now. I did my last video on rotators, which are similar. How that logic works. All right. So, what happens when you press a button? What happens under the hood when you press a button on a digital device? How does it get to where it's going? Is it smooth? Nope. All right, what happens is this raw button signal, it doesn't look like this, like, hey, low, we're going from low signal to high signal. It's like this. All over the place. So you got to smooth that out. How do you smooth that out? Because if you don't, the edge detector does what? It goes text from 0 to high, like this. Or it texts from high to low. Low to high, high to low. This one is a positive edge. We'll see more about that later. But here's a bunch of edges. And at 100 megahertz, you'd have millions of signals that are going into and this shift rotator goes to the light. So you'd have a whole bunch of your light going blah, 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 going all over crazy all over the place, just like that thing just did. All right, so we need a debouncer, and I'll show you how to do that. Come on, Mr. Debouncer. Debouncer output. Things are gonna get big around here in the heart of the city. All right. Debouncer output. So it waits an amount of time. Let's say it waits 10 microseconds. As this is going bonkers, all of a sudden the signal stabilizes. So at 10 microseconds, boom, it goes stable. And now that's what this debouncer is meant to do. That's what the logic is meant to do. To find when that signal stabilizes. And I'll show you the code behind it, how the logic works. But first we'll talk about with the edge detector. output does. Now the edge detector is a one cycle, one clock pulse. So it's going to go, see, boom, high. That's when the clock edge goes high, and it says that pulse to the shift. Why do I say register? Shift register, which then goes to whatever you program that to do. That might go to multiple lights, turn multiple lights on. It might flicker the light, strobe the light, pulse the light, whatever your logic is that you want to do. So, how does this debouncer work? How does the logic behind it work? So let's just say it's a counter. The debouncer is a counter. So it counts. If the current input is equal to the previous input, if the current input is equal to previous input, the counter counts. Else, the counter doesn't count. Now, remember I said something about the 10 microseconds. It's got to wait. It has a time. It doesn't go at any time because it wouldn't know. You have to program it. So if the counter counts from your counter is maxed out at 10, if the counter is at its max value, then the debounced output, non-blocking assignment, previous input, current input. So your current input. That's correct. So remember, the edge detector is a pulse. And then this, the debouncer, it's waiting for a level. It's waiting for a level signal. That's how you'd say it. It's waiting for this level signal. And the edge detector is waiting for, it's really just waiting for its edge, waiting for it, the signal to go high. And then it sends a pulse out. And then that input will be the debounced output. Because remember, the debounced output will be that very first one right here when it goes level. And that's the logic behind it. That's it. Deuces.